In this video we are going to discuss laws of sets theory. So first let us talk about idempotent laws. There are two laws. One is A union A is equal to A. Set A union set A is equal to A. That is, if we take union of a set with itself, the result is the set itself. And the second idempotent law is A intersection A is equal to A. That is, if we take intersection of any set with itself, the result is the set itself. Now we are going to prove the first law, that is A union A is equal to A. So by definition, A union A is a set of X such that X belongs to A or X belongs to A. Basically, wherever you see union of sets, we use the word or, and for intersection we use the word and. These 2 points must be kept in mind well. So there is union between A and A, so we used the word or. So A union A is a set of X such that X belongs to A or X belongs to A. Clearly, there is a repetition of the same statement, X belongs to A or X belongs to A. These two statements are identical, so we may write these two repeated statements only once as X such that X belongs to A. And by definition, this is the set A itself. A set of X such that X belongs to A, that is the set A. So we have proved that A union A is equal to A. Now let's prove the second idempotent law, that is A intersection A is equal to A. So by definition, A intersection A is a set of X such that X belongs to A intersection, then we have to use the word and, X belongs to A. Because in intersection we take the common element, so if an element belongs to intersection of the two sets, that must belong both of the sets. So we use the word and. X belongs to A, the first set, and X must also belongs to second set, which is also A. So we write X belongs to A and X belongs to A. Again, this is the repetition of the same statement, so we may write it as X set of X such that X belongs to A. Again, by definition, this is the set A. So we have proved the second idempotent law. Now the second laws are identity laws. Identity laws are also two laws. First identity law is A union phi is equal to A, and the second identity law is A intersection U is equal to A, where phi is a null set and capital U is a universal set. Now we are going to prove the first identity law, that is A union phi is equal to A. So by definition, A union phi is a set of X such that X belongs to either of these two sets. So we may write X belongs to A for union or X belongs to phi. And if we observe this statement attentively, what we may infer from this, x belongs to A or x belongs to phi, and as you know, phi is a null set which has no element. So x may not belong to phi. So this statement is equivalent to the statement a set of x such that x belongs to A. Again, this is the definition of set A, a set of x where x belongs to A, that is the set A itself. So we have proved that A union phi is equal to set A itself. So we have proved first identity law. Now we are going to prove the second identity law, which is A intersection U is equal to A. A intersection universal set U is equal to A. By definition, A intersection universal set is a set of x such that x belongs to A and, because there is intersection, and for intersection we use the word and because if an element belongs to A intersection U, that must belong both of the sets. So we should say x belongs to A and x must belongs to universal set U. And since universal set must have all the elements of A, and there may be some other elements which are not in A, and if an element belongs both of these two sets, that is belongs to A and belongs to universal set, that must belongs to A because A as a whole is contained by universal set. So for this statement we may write only a set of x such that x belongs to A, because if an element belongs to A, that must belongs to universal set because universal set contains all the elements of A. So this is sufficient to write the set of x such that x belongs to A, and again by definition this is the set A itself. So we have proved that A intersection U is equal to A. Before going ahead, it is very important to recall one important property which we have discussed in the case of subsets, that if two sets are equal, then those sets must be subset of each other, because A contains all the elements of B and B contains all the elements of A, and by the definition of a subset, if A contains all the elements of B, then B is said to be subset of A, and if B contains all the elements of A, then A is said to be a subset of A. So if we need to prove two sets equal to each other, we have to prove that these sets are subset of each other. A is a subset of B and B is a subset of A, then it is sufficient to prove that both the sets A and B are equal to each other. Now we move on to the third laws of sets theory, which are commutative laws. The first commutative law is A union B is equal to B union A. That is, in the case of union of two sets, the sequence of the sets is not taken into account. And the second one is A intersection B is equal to B intersection A. So similarly, as the sequence of sets in the case of union is not important, in the case of intersection too, the sequence of the sets doesn't matter. So we are going to prove the first commutative law, that is A union B is equal to B union A. To prove this law, we take an arbitrary element x which belongs to A union B. We let x belongs to A union B to the left hand side, and by definition it implies that x belongs to A for union B. Use or word x belongs to B. So x belongs to A union B, then x belongs to A or x belongs to B. It implies that you know well this statement may also be written as x belongs to B or x belongs to A. It implies that, and if we write this statement back in the form of union, we may also write it as x belongs to B union A because of the word or. X belongs to B or, that is union A. X belongs to A. So x belongs to B union A. So we have taken arbitrary element x belongs to A union B, and we have proved that x belongs to B union A. That is, if x belongs to A union B, that must also belongs to B union A. So from this we infer that A union B is a subset of B union A. Let it be equation number 1. Now let y belongs to B union A. Now we take an arbitrary element from the right hand side, that is B union A, and again, as we have done for A union B, this statement may be written as x belongs to B or y belongs to B or y belongs to A. It implies that the same statement may also be written as y belongs to A or y belongs to B. It implies that if we write this statement collectively, we may write it as y belongs to A union B because of the word or. We use union operation. So we have taken an arbitrary element y from B union A, and we have proved that y must also belongs to A union B. So we infer from this that B union A is a subset of A union B. I repeat, if y belongs to B union A, it must also belongs to A union B. That means A union B must contain all the elements of B union A. So we may write it as B union A is a subset of A union B. Let it be equation number 1. So if we compare the equation number 1 and 2, A union B is a subset of B union A and B union A is a subset of A union B. So it is only possible when A union B and B union A are equal sets. So we may write it as from 1 and 2. A union B is equal to B union A. That's it. We have proved first commutative law. Now the second commutative law, you better try yourself. Now the next laws are associative laws. The first associative law is A union B grouped in a parenthesis union C is equal to A union parenthesis B union C. And the second associative law is parenthesis A intersection B intersection C is equal to A intersection parenthesis B intersection C. So now we are going to prove the first associative law. So let X belongs to A union B union C. Now we have taken an arbitrary element X belonging to the left hand side A union B union C. it implies that by definition we may write it as X belongs to A union B or X belongs to C. We have used OR for this union operation. So next, X belongs to A union B may also be written as X belongs to A or X belongs to B. And the next, this or as it is, this X belongs to C as it is. So in the next step, we may write it as X belongs to A as it is or as it is, and we combine these two statements as X belongs to B union C. So it implies that now we may combine these two statements for the word OR. So it implies X belongs to A union for OR B union C. So taking an arbitrary element from A union B parenthesis union C, we have proved that X belongs to A union parenthesis B union C. That means if X belongs to A parenthesis A union B union C, it must belongs to A union parenthesis B union C. So it implies that this set is a subset of this set. So A union B union C is a subset of A union B union C. Let it be equation number 1. Now we take another arbitrary element Y belonging to the right hand side this time, A union B union C. So again we may write it as Y belongs to A or Y belongs to parenthesis B union C. It implies that Y belongs to A or as it is, and now expand this statement as Y belongs to B or Y belongs to C. Now in the next step we may combine these two statements as Y belongs to A union B and or as it is, and Y belongs to C as it is. In the next step we may combine these two statements for the word OR. Y belongs to A union B. For OR we may write union Y. So we have taken Y as an arbitrary element of A union B union C, and it implies that Y belongs to A union B union C. It means if Y belongs to this set, it must also belongs to this set. So we may infer from this as A union B union C, that is this set is a subset of this set A union B union C. So let it be equation number 2. Now if we observe equation number 1 and equation number 2, A union B union C is a subset of A union parenthesis B union C, and from 2 A union parenthesis B union C is a subset of parenthesis A union B union C. So this is only possible when these two sets are equal to each other from 1 and 2. We get A parenthesis A union B union C is equal to A union parenthesis B union C. So in this way we prove the first associative law. Now the second associative law you should try yourself. Now the next laws to be discussed are distributive laws. The first distributive law is A union parenthesis B intersection C is equal to parenthesis A union B intersection parenthesis A union C, and the second distributive law is A intersection parenthesis B union C is equal to parenthesis A intersection B union parenthesis A intersection C. Now we are going to prove the first distributive law, that is A union parenthesis B intersection C is equal to parenthesis A union B intersection parenthesis A union C. So let X belongs to A union parenthesis B intersection C. We have taken an arbitrary element X from A union B intersection C. It implies that X belongs to A, and for this union we may take the word or. X belongs to parenthesis B intersection C. It implies that X belongs to A as it is or as it is, and we may write this statement as X belongs to B, and for this intersection we may use AND word, X belongs to C. X belongs to B intersection C implies that X belongs to B and X belongs to C. It implies that. Now we may write this statement as in two parts, X belongs to A or X belongs to B, and X belongs to A or X belongs to C. Now it implies that this statement may be written as X belongs to A union B within parentheses. Because of OR word we use the operation union, and this AND as it is, and these two statements may also be written as X belongs to A union C because of this word OR. It implies that. Now these two statements are connected with AND, so these two statements may be written as X belongs to parenthesis A union B intersection for AND parenthesis A union C. So we have taken an arbitrary element X from A union parenthesis B intersection C, and we have proved that X belongs to A union B intersection A union C. It means A union B intersection C is a subset of parenthesis A union B intersection A parenthesis A union C. Let it be equation number 1. Similarly, we may prove that A union B intersection A union C is a subset of A union B intersection C, taking Y as an arbitrary element from right hand side, as we have done in the case of associative laws and commutative laws. So from these two results, if this set is a subset of this set and this set is a subset of this set, it implies that both the sets must be equal. So from 1 and 2, you may write A union B intersection C is equal to A union B intersection A union C. That's proved. So we have proved the first distributive law in this way, and now you should try the second distributive law yourself. Now the next laws to be discussed are De Morgan's laws. the first De Morgan law is A union B complement is equal to A complement intersection B complement. That is, if there is union inside the parenthesis whose complement we have taken, then on the right hand side there should be intersection between their individual complements. And the second one is parenthesis A intersection B complement is equal to A complement union B complement. Again, if inside the bracket there is intersection operation whose complement we have to take, that is equal to the union of the individual complements of the sets. So these are called De Morgan's law, and we are going to prove the first De Morgan law. Let X belongs to A union B complement. It implies that X does not belong to A union B. As you know, the complement of a set is a set which contains all the elements of universal set which are not in the set itself whose complement we are taking. So if X belongs to A union B complement, that may not be in the set A union B. So if X belongs to A union B complement, then X must not belong to A union B. It implies that X does not belong to A, and for the symbol is does not belong to, for union operation we use the word and for the operation intersection we use the word or. This process is reversed. As for the symbol belongs to, union means or and intersection means and. For does not belong to, union means and intersection means or. So X does not belong to A union B, we may write it as X belongs to A and X does not belongs to B. It implies that. Now as you see, if X does not belong to A, X must belongs to A complement, and if X is not an element of B, X must be an element of B complement. So X belongs to B complement. Now because these symbols are belongs to, now N stands for intersection, so implies that X belongs to A complement intersection B complement. So if X belongs to parenthesis A union B complement, then it must belong to A complement intersection B complement. It implies that A union B complement is a subset of A complement intersection B complement. Let it be equation number 1. And now in the same way we may prove that A complement intersection B complement is a subset of A union B complement, and we will make it as equation number 2, and then comparing the equation 1 and 2 from equation from 1 and 2, A union B complement is equal to A complement intersection B complement, because it is only possible when these two sets are equal to each other, that this is a subset of this and this is a subset of this. So in this way we have proved the first De Morgan's law, and the second De Morgan's law you should try yourself.